Real number.
In mathematics, a real number is a value that represents a quantity along a continuous line. The real numbers include all the rational numbers, such as the integer 5 and the fraction 4/3, and all the irrational numbers such as 2 and p. Real numbers can be thought of as points on an infinitely long line called the number line or real line, where the points corresponding to integers are equally spaced. Any real number can be determined by a possibly infinite decimal representation such as that of 8.632, where each consecutive digit is measured in units 1/10 the size of the previous one. The real line can be thought of as a part of the complex plane, and complex numbers include real numbers. These descriptions of the real numbers are not sufficiently rigorous by the modern standards of pure mathematics. The discovery of a suitably rigorous definition of the real numbers, indeed, the realization that a better definition was needed, was one of the most important developments of 19th-century mathematics. The currently standard axiomatic definition is that real numbers form the unique Archimedean complete totally ordered field, R plus less than, up to an isomorphism, whereas popular constructive definitions of real numbers include declaring them as equivalence classes of Cauchy sequences of rational numbers, Dedekind cuts, or certain infinite decimal representations, together with precise interpretations for the arithmetic operations and the order relation. These definitions are equivalent in the realm of classical mathematics. The reals are uncountable. That is, while both the set of all natural numbers and the set of all real numbers are infinite sets, there can be no one-to-one function from the real numbers to the natural numbers. The cardinality of the set of all real numbers, denoted and called cardinality of the continuum, is strictly greater than the cardinality of the set of all natural numbers, denoted. The statement that there is no subset of the reals with cardinality strictly greater than and strictly smaller than is known as the continuum hypothesis. It is known to be neither provable nor refutable using the axioms of Zermelo-Fraenkel set theory, the standard foundation of modern mathematics, provided ZF set theory is consistent.
Basic properties.
A real number may be either rational or irrational, either algebraic or transcendental, and either positive, negative, or zero. Real numbers are used to measure continuous quantities. They may be expressed by decimal representations that have an infinite sequence of digits to the right of the decimal point. These are often represented in the same form as 324.823122147. The ellipsis, 3 dots, indicates that there would still be more digits to come. More formally, real numbers have the two basic properties of being an ordered field, and having the least upper bound property. The first says that real numbers comprise a field, with addition and multiplication as well as division by non-zero numbers, which can be totally ordered on a number line in a way compatible with addition and multiplication. The second says that, if a non-empty set of real numbers has an upper bound, then it has a real least upper bound. The second condition distinguishes the real numbers from the rational numbers. For example, the set of rational numbers whose square is less than 2 is a set with an upper bound, for example 1.5, but no rational least upper bound, hence the rational numbers do not satisfy the least upper bound property.
In physics.
In the physical sciences, most physical constants such as the universal gravitational constant, and physical variables, such as position, mass, speed, and electric charge, are modeled using real numbers. In fact, the fundamental physical theories such as classical mechanics, electromagnetism, quantum mechanics, general relativity and the Standard Model are described using mathematical structures, typically smooth manifolds or Hilbert spaces, that are based on the real numbers, although actual measurements of physical quantities are of finite accuracy and precision. In some recent developments of theoretical physics stemming from the holographic principle, the universe is seen fundamentally as an information store, essentially zeros and ones, organized in much less geometrical fashion and manifesting itself as space-time and particle fields only on a more superficial level. This approach removes the real number system from its foundational role in physics and even prohibits the existence of infinite precision real numbers in the physical universe by considerations based on the Beekenstein bound.
In computation,
with some exceptions, most calculators do not operate on real numbers. Instead, they work with finite precision approximations called floating-point numbers. In fact, most scientific computation uses floating-point arithmetic. Real numbers satisfy the usual rules of arithmetic, but floating-point numbers do not. Computers cannot directly store arbitrary real numbers with infinitely many digits. The precision is limited by the number of bits allocated to store a number, whether as floating-point numbers or arbitrary precision numbers. However, computer algebra systems can operate on irrational quantities exactly by manipulating formulas for them, such as OR, rather than their rational or decimal approximation. However, it is not in general possible to determine whether two such expressions are equal, the constant problem. A real number is called computable if there exists an algorithm that yields its digits. Because there are only countably many algorithms, but an uncountable number of reals, almost all real numbers fail to be computable. Moreover, the equality of two computable numbers is an undecidable problem. Some constructivists accept the existence of only those reals that are computable. The set of definable numbers is broader, but still only countable.
vocabulary and notations.
Mathematicians use the symbol R, or, alternatively the letter R in Blackboard Bold, Unicode, U+211D, named double-struck capital R, to represent the set of all real numbers. As this set is naturally endowed with the structure of a field, the expression field of real numbers is frequently used when its algebraic properties are under consideration. The sets of positive real numbers and negative real numbers are often denoted by a plus and R, respectively. R plus and R are also used. The non-negative real numbers can be denoted by R. 0 but 1 often sees this set simply denoted by a plus. 0. In French mathematics, the set of positive real numbers and a set of negative real numbers include 0, they are noted respectively plus and. In this understanding, the respective sets without 0 are called strictly positive real numbers and strictly negative real numbers, and are noted plus and. The notation Rn refers to the Cartesian product of n copies of R, which is an n-dimensional vector space over the field of the real numbers. This vector space may be identified to the n-dimensional space of Euclidean geometry as soon as a coordinate system has been chosen in the latter. For example, a value from R3 consists of 3 real numbers and specifies the coordinates of a point in 3-dimensional space. In mathematics, real is used as an adjective, meaning that the underlying field is the field of the real numbers, or the real field. For example, real matrix, real polynomial and real Lie algebra. As a substantive, the word real is used almost strictly in reference to the real numbers themselves, for example, the set of all reals.
History.
Simple fractions have been used by the Egyptians around 1000 BC. The Vedic Sulbas Sutras, the rules of Khwarizm, c. 600 BC, include what may be the first use of irrational numbers. The concept of irrationality was implicitly accepted by early Indian mathematicians since Manava, c. 750-690 BC, who were aware that the square roots of certain numbers such as 2 and 61 could not be exactly determined. Around 500 BC, the Greek mathematicians led by Pythagoras realized the need for irrational numbers, in particular the irrationality of the square root of 2. The Middle Ages brought the acceptance of 0, negative, integral, and fractional numbers, first by Indian and Chinese mathematicians, and then by Arabic mathematicians, who were also the first to treat irrational numbers as algebraic objects, which was made possible by the development of algebra. Arabic mathematicians merged the concepts of number and magnitude into a more general idea of real numbers. The Egyptian mathematician Abu Kamil Shujaa ibn Islam, c. 850-930, was the first to accept irrational numbers as solutions to quadratic equations or as coefficients in an equation, often in the form of square roots, cube roots and fourth roots. In the 16th century, Simon Stevin created the basis for modern decimal notation, and insisted that there is no difference between rational and irrational numbers in this regard. In the 17th century, Descartes introduced the term real to describe roots of a polynomial, distinguishing them from imaginary ones. In the 18th and 19th centuries there was much work on irrational and transcendental numbers. Johann Heinrich Lambert, 1761, gave the first flawed proof that P cannot be rational. Adrien Marie Legendre, 1794, completed the proof, and showed that P is not the square root of a rational number. Paolo Ruffini, 1799, and Niels Henrik Abel, 1842, both constructed proofs of the Abel-Ruffini theorem, that the general quintic or higher equations cannot be solved by a general formula involving only arithmetical operations and roots. Evarist Galois, 1832, developed techniques for determining whether a given equation could be solved by radicals, which gave rise to the field of Galois theory. Joseph Liouville, 1840, showed that neither E nor E2 can be a root of an integer quadratic equation, and then established the existence of transcendental numbers, the proof being subsequently displaced by Georg Cantor, 1873. Charles Hermite, 1873, first proved that E is transcendental, and Ferdinand von Lindemann, 1882, showed that P is transcendental. Lindemann's proof was much simplified by Weierstrass, 1885, still further by David Hilbert, 1893, and has finally been made elementary by Adolf Hurwitz and Paul Gordon. The development of calculus in the 18th century used the entire set of real numbers without having defined them cleanly. The first rigorous definition was given by Georg Cantor in 1871. In 1874 he showed that the set of all real numbers is uncountably infinite but the set of all algebraic numbers is countably infinite. Contrary to widely held beliefs, his first method was not his famous diagonal argument, which he published in 1891. See Cantor's first uncountability proof.
Definition.
The real number system can be defined axiomatically up to an isomorphism, which is described below. There are also many ways to construct the real number system, for example, starting from natural numbers, then defining rational numbers algebraically, and finally defining real numbers as equivalence classes of their Cauchy sequences or as Dedekind cuts, which are certain subsets of rational numbers. Another possibility is to start from some rigorous axiomatization of Euclidean geometry, Hilbert, Tarski etc. and then define the real number system geometrically. From the structuralist point of view all these constructions are on equal footing.
Axiomatic approach.
Let denote the set of all real numbers. Then, the set is a field, meaning that addition and multiplication are defined and have the usual properties. The field is ordered, meaning that there is a total order. Such that, for all real numbers x, y and z. If x, y then x plus z. Y plus z. If x, 0 and y. 0 then xy. 0, if x, y then x plus z. Y plus z, if x, 0 and y. 0 then xy. 0. The order is Dedekind complete. That is, every non-empty subset S of with an upper bound in has a least upper bound, also called supremum, in. The last property is what differentiates the reals from the rationals. For example, the set of rationals with square less than 2 has a rational upper bound, for example, 1.5 but no rational least upper bound, because the square root of 2 is not rational. The real numbers are uniquely specified by the above properties. More precisely, given any two Dedekind complete ordered fields 1 and 2, there exists a unique field isomorphism from 1 to 2, allowing us to think of them as essentially the same mathematical object. For another axiomatization of, see Tarski's axiomatization of the reals.
Construction from the rational numbers.
The real numbers can be constructed as a completion of the rational numbers in such a way that a sequence defined by a decimal or binary expansion like 3, 3.1, 3.14, 3.141, 3.1415 converges to a unique real number, in this case p. For details and other constructions of real numbers, see construction of the real numbers.
Properties. Completeness.
A main reason for using real numbers is that the reals contain all limits. More precisely, every sequence of real numbers having the property that consecutive terms of the sequence become arbitrarily close to each other necessarily has the property that after some term in the sequence the remaining terms are arbitrarily close to some specific real number. In mathematical terminology, this means that the reals are complete, in the sense of metric spaces or uniform spaces, which is a different sense than the Dedekind completeness of the order in the previous section. This is formally defined in the following way. A sequence, xn, of real numbers is called a Cauchy sequence if for any e greater than 0 there exists an integer n, possibly depending on e, such that the distance xn. xm is less than e for all n and m that are both greater than n. In other words, a sequence is a Cauchy sequence if its elements xn eventually come and remain arbitrarily close to each other. A sequence, xn, converges to the limit x if for any e greater than 0 there exists an integer n, possibly depending on e, such that the distance xn. x is less than e provided that n is greater than n. In other words, a sequence has limit x if its elements eventually come and remain arbitrarily close to x. Notice that every convergent sequence is a Cauchy sequence. The converse is also true. That is, the reals are complete. Note that the rationals are not complete. For example, the sequence 1, 1.4, 1.41, 1.414, 1.4142, 1.41421, where each term adds a digit of the decimal expansion of the positive square root of 2, is Cauchy but it does not converge to a rational number. In the real numbers, in contrast, it converges to the positive square root of 2. The existence of limits of Cauchy sequences is what makes calculus work and is of great practical use. The standard numerical test to determine if a sequence has a limit is to test if it is a Cauchy sequence, as the limit is typically not known in advance. For example, the standard series of the exponential function converges to a real number because for every x the sums can be made arbitrarily small by choosing n sufficiently large. This proves that the sequence is Cauchy, so we know that the sequence converges even if the limit is not known in advance.
The complete ordered field.
The real numbers are often described as the complete ordered field, a phrase that can be interpreted in several ways. First, an order can be lattice complete. It is easy to see that no ordered field can be lattice complete, because it can have no largest element, given any element z, z plus 1 is larger, so this is not the sense that is meant. Additionally, an order can be Dedekind complete, as defined in the section axioms. The uniqueness result at the end of that section justifies using the word the in the phrase complete ordered field, when this is the sense of complete that is meant. This sense of completeness is most closely related to the construction of the reals from Dedekind cuts, since that construction starts from an ordered field, the rationals, and then forms the Dedekind completion of it in a standard way. These two notions of completeness ignore the field structure. However, an ordered group, in this case, the additive group of the field, defines a uniform structure, and uniform structures have a notion of completeness, topology. The description in the section completeness above is a special case. We refer to the notion of completeness in uniform spaces rather than the related and better-known notion for metric spaces, since the definition of metric space relies on already having a characterization of the real numbers. It is not true that R is the only uniformly complete ordered field, but it is the only uniformly complete Archimedean field, and indeed one often hears the phrase complete Archimedean field instead of complete ordered field. Every uniformly complete Archimedean field must also be Dedekind complete, and vice versa, of course, justifying using the in the phrase the complete Archimedean field. This sense of completeness is most closely related to the construction of the reals from Cauchy sequences, the construction carried out in full in this article, since it starts with an Archimedean field, the rationals, and forms the uniform completion of it in a standard way. But the original use of the phrase complete Archimedean field was by David Hilbert, who meant still something else by it. He meant that the real numbers form the largest Archimedean field in the sense that every other Archimedean field is a subfield of R. Thus R is complete in the sense that nothing further can be added to it without making it no longer an Archimedean field. This sense of completeness is most closely related to the construction of the reals from surreal numbers, since that construction starts with a proper class that contains every ordered field, the surreals, and then selects from it the largest Archimedean subfield.
Advanced properties.
The reals are uncountable. That is, there are strictly more real numbers than natural numbers, even though both sets are infinite. In fact, the cardinality of the reals equals that of the set of subsets, that is, the power set, of the natural numbers, and Cantor's diagonal argument states that the latter set's cardinality is strictly greater than the cardinality of n. Since only a countable set of real numbers can be algebraic, almost all real numbers are transcendental. The non-existence of a subset of the reals with cardinality strictly between that of the integers and the reals is known as the continuum hypothesis. The continuum hypothesis can neither be proved nor be disproved. It is independent from the axioms of set theory. As a topological space, the real numbers are separable. This is because the set of rationals, which is countable, is dense in the real numbers. The irrational numbers are also dense in the real numbers, however they are uncountable and have the same cardinality as the reals. The real numbers form a metric space. The distance between x and y is defined as the absolute value x, y. By virtue of being a totally ordered set, they also carry an order topology. The topology arising from the metric and the one arising from the order are identical, but yield different presentations for the topology. In the order topology is ordered intervals, in the metric topology is epsilon balls. The Dedekind cuts construction uses the order topology presentation, while the Cauchy sequences construction uses the metric topology presentation. The reals are a contractible, hence connected and simply connected, separable and complete metric space of Hausdorff dimension 1. The real numbers are locally compact but not compact. There are various properties that uniquely specify them. For instance, all unbounded, connected, and separable order topologies are necessarily homeomorphic to the reals. Every non-negative real number has a square root in R, although no negative number does. This shows that the order on R is determined by its algebraic structure. Also, every polynomial of odd degree admits at least one real root. These two properties make R the premier example of a real closed field. Proving this is the first half of one proof of the fundamental theorem of algebra. The reals carry a canonical measure, the Lebesgue measure, which is the Haar measure on their structure as a topological group normalized such that the unit interval has measure 1. There exist sets of real numbers that are not Lebesgue measurable, for example Vitali sets. The supremum axiom of the reals refers to subsets of the reals and is therefore a second-order logical statement. It is not possible to characterize the reals with first-order logic alone. The Lowenheim-Scullum theorem implies that there exists a countable dense subset of the real numbers satisfying exactly the same sentences in first-order logic as the real numbers themselves. The set of hyperreal numbers satisfies the same first-order sentences as are ordered fields that satisfy the same first-order sentences as are called non-standard models of R. This is what makes non-standard analysis work. By proving a first-order statement in some non-standard model, which may be easier than proving it in R, we know that the same statement must also be true of R. A field R of real numbers is an extension field of the field Q of rational numbers, and R can therefore be seen as a vector space over Q. Zermelo-Fraenkel set theory with the axiom of choice guarantees the existence of a basis of this vector space, there exists a set B of real numbers such that every real number can be written uniquely as a finite linear combination of elements of this set, using rational coefficients only, and such that no element of B is a rational linear combination of the others. However, this existence theorem is purely theoretical, as such a base has never been explicitly described. The well-ordering theorem implies that the real numbers can be well-ordered if the axiom of choice is assumed. There exists a total order on A with a property that every non-empty subset of A has a least element in this ordering. The standard ordering of the real numbers is not a well-ordering since, for example, an open interval does not contain a least element in this ordering. Again, the existence of such a well-ordering is purely theoretical, as it cannot be explicitly described.
Generalizations and extensions.
The real numbers can be generalized and extended in several different directions. The complex numbers contain solutions to all polynomial equations and hence are an algebraically closed field unlike the real numbers. However, the complex numbers are not an ordered field. The affinely extended real number system adds two elements plus and. It is a compact space. It is no longer a field, not even an additive group, but it still has a total order. Moreover, it is a complete lattice. The real projective line adds only one value. It is also a compact space. Again, it is no longer a field, not even an additive group. However, it allows division of a non-zero element by zero. It is not ordered anymore. The long real line pastes together 1 plus 1 copies of the real line plus a single point. Here 1 denotes the reversed ordering of 1, to create an ordered set that is locally identical to the real numbers, but somehow longer. For instance, there is an order-preserving embedding of 1 inch the long real line but not in the real numbers. The long real line is the largest ordered set that is complete and locally Archimedean. As with the previous two examples, this set is no longer a field or additive group. Ordered fields extending the reals are the hyperreal numbers and the surreal numbers. Both of them contain infinitesimal and infinitely large numbers and are therefore non-Archimedean ordered fields. Self-adjoint operators on a Hilbert space, for example, self-adjoint square complex matrices, generalize the reals in many respects. They can be ordered, though not totally ordered. They are complete, all their eigenvalues are real and they form a real associative algebra. Positive definite operators correspond to the positive reals and normal operators correspond to the complex numbers.
Reals and set theory.
In set theory, specifically descriptive set theory, the bias space is used as a surrogate for the real numbers since the latter have some topological properties, connectedness, that are a technical inconvenience. Elements of bias space are referred to as reals.
Real numbers and logic.
The real numbers are most often formalized using the Zermelo-Fraenkel axiomatization of set theory, but some mathematicians study the real numbers with other logical foundations of mathematics. In particular, the real numbers are also studied in reverse mathematics and in constructive mathematics. The hyperreal numbers as developed by Edwin Hewitt, Abraham Robinson and others extend the set of the real numbers by introducing infinitesimal and infinite numbers, allowing for building infinitesimal calculus in a way closer to the original intuitions of Leibniz, Euler, Cauchy and others. Edward Nelson's internal set theory enriches the Zermelo-Fraenkel set theory syntactically by introducing a unary predicate standard. In this approach, infinitesimals are non-standard elements of the set of the real numbers, rather than being elements of an extension thereof, as in Robinson's theory. The continuum hypothesis posits that the cardinality of the set of the real numbers is that is the smallest infinite cardinal number after the cardinality of the integers. Paul Cohen proved in 1963 that it is an axiom independent of the other axioms of set theory. That is, one may choose either the continuum hypothesis or its negation as an axiom of set theory, without contradiction.